All right, so super quick on these notes. Remember, the last set of notes is about angle measures only, and now it's about side measures. But then, part of the side measure thing has to do with inscribed and circumscribed. So we're going to start with that. Go ahead and mark those letters down. Not that I needed them, but I guess we're not going to use this as a numerical example, but as a definition. So it depends upon who you're talking about. If I'm talking about the circle, then the circle, it's inside the triangle, so it inscribes. So this is just a term, and I'm going to put the word inside like as a way to remember that. So the circle inscribes the triangle. I don't want to spend too much time on this. We want to get to like what do you have to worry about on that obnoxious worksheet I gave you. Okay. Um, and then so if I reversed it though, then the word circumscribed would be used. So the triangle circumscribes the circle. So it's back and forth because I'll show you that more so on the next example. So okay, I gave the word away. This is the circle circumscribing. Now, one word I can think of, circumscribe, is circumnavigate. Okay, circumnavigate is what Magellan was given credit for. Not that he may have been the first one to do that. History, a little blurry on that. Circumscribe means go around the outside. So the circle circumscribes the triangle. Oh, then I do have to go back and mark something on this last one. But let's look at this first. You already know something about this. Okay, if I reverse it, the triangle is inscribed in the circle because we already know I'm going to pick angle B. What is angle B called? Let's just take the angle. We already have that as a definition. What is that called? And I already used the word. It starts with an I. It's an inscribed angle. What is that angle compared to its arc it intersects? Is it equal or is it half? I have no time. It's half. Okay, the angle is half because this angle is equal, the central angle. And I always want you to think about that. That central angle is equal to that arc it cuts. Think of a rubber band. If I pulled that vertex to B, then it really stretches that angle out and shrinks it and makes it, and it's actually half. Something to remember. Oh, my bad, dogs. No, this is kind of bad. We're just throwing you some information here, but this is actually pretty easy. On this inscribed situation, actually, we have a special situation that those are three tangent lines, right? Isn't that triangle three tangent lines? These are called common external tangents. These are common, external tangents, and these are. And you can look at them, and doesn't it look like they are of equal measure for each color? They are. So go ahead and mark those as equal. If this was a traditional geometry class, we'd write this as a theorem and then use it in a proof. And you may have seen this before. I know you did a lot of proofs last year, so just maybe it's a reminder. Okay, so I threw this as an example with no numbers. Let's throw the numbers down now. Let's say this is 3 units. Let's say this whole thing is 10 units. And then let's say this one is 4 units. Same numbers, I think, in all 4 classes I used. I like calling this a walk around problem. We'll call this a perimeter. What is the perimeter? And then just exercising that word again. Perimeter is distance around an object of triangle JKL, the whole thing. All right. Well, I like calling this a walk around problem because, just for purposes of time, and we are really short here, we would know that that's 3 because those are common external tangents. What does that make BA? Is that an A? Oh, that's a K. Wow. I looked at it from far away. That's how bad my eyes are. Sorry. BK. What's BK? Right here. 7. And then kind of get rid of that as a distractor so you don't double use that number. And then that makes this 7 and that makes this 4. So kind of a walk around situation. And then you add up all those sides. So 10 plus 11 plus 7. The perimeter is 28. Again, I didn't use labels, so just say 28 units. Okay. All right, so now let's look at this. Don't mark this, but go ahead and put the letters. I gave you a letterless example. And then look at this globally, and we'll get those other letters for this as well. It's the same thing with the angle measures, that this chord is separated from the other three drawings. And the other three drawings will have the same situation going on with them, just like with the angle measures, and we'll talk about that. Let's talk about the angles real quick, but don't write anything down because we already have this. If I pick this angle, the two arcs in question are these then. And that angle is half of, what do I do with those arcs? Add them or subtract them? Add them. So you just got to remember that. Add them up. Add them up. Whereas, let's color this green. What do we do with these two arcs? What do we do with those two arcs? Subtract. So it's half of minus, big minus small. And then that's the same for all of these. Half of big minus small. Half of big minus small. That does encompass a whole. That's old school. You already had that as notes. Now we got to talk about segments and what are the segment lengths. Now I can approach this in two different ways, and I am going to approach it in two different ways. I like the first one with this chord situation, thinking about proportions, just like in triangles, and this may be easy for you. But when a chord intersects another chord, then those chords are cut proportionally. And you can either go top over bottom equals top over bottom, or stay on the top, left over right equals left over right. And then that seems like what we did with triangles. So I'm going to go top on the left, AE, over bottom, DE. And that equals top, EB, on the right, over bottom, EC. Or another way you can think of it, my pen keeps not writing. I love this computer. All right. Another episode of Samuel's Fighting Technology. Cross multiply, and you end up getting AE, sorry for that, times EC. So another way you would see this in a geometry book, that's 3 times I tried to write that C. AE times EC equals DE times EB. So this part of the segment times this part equals this part times this part. Any way you got to do it, you got to get the right, thing here. I think it's easier just to think of them proportionally. All right. Stay on the left, top over bottom equals stay on the right, top over bottom, and then crisscross and solve. So whatever book you look at, they will approach that two different ways. Now, in this section, all three of these can be derived by the same formula. And here it is in words. You ready? In this section, outside pen times whole, and I'm going to jump to the secant first, equals outside times whole. What? Watch on the secant. It's best here. Then I'm going to go to the secant tangent. Remember, that is a secant line and another secant line, right? Okay. So here's outside. And if you have a highlighter, go ahead and mark this up later. This will really resonate with you. Here's the outside of that secant line. It's AB. Here's the whole of this secant line, AC. Outside times whole equals, I lost my thing again, the marker. Outside times whole. So I'm going to write that down as a mathematical statement. Outside AB times the whole all the way from A to C equals the other segment, A D times AE. So frustrating. Okay, so AB times AC equals AD times AE. Outside times whole equals outside times whole. This is what's true for these situations. Let's go to the secant tangent. What? Okay, the bottom one's easy. Outside times whole. Okay, so let's write that down first because that one made sense compared. Not that it makes sense, it's something to memorize, and I could do that again since I showed you the first one. Interesting. AC times AD, and that equals, wait a minute, all of this is on the outside. Who cares? Outside times whole. What does that mean? I'm doing the AB, squaring it. So you could write AB times AB if it helps you. All right, but it just is AB squared. All right, true. Proportions is why this is possible and we can do what we're doing here. Alrighty then. Oh no. Didn't I already just tell you this though? That's a common external tangent. So what do you know about these two segments anyway? They're equal. But we could play outside times whole equals outside times whole, just like with the tangents. But why would we do that? That just means AB has to equal AC and kind of lightly cross that off. But just so you know that it is the outside times whole equals outside times whole kind of scenario there. All right, so we already know that's a common external tangent, no big deal. All right, we only have 3 minutes. So I will just set this one up real quick. You see this? You see this secant secant? So it's 6 times, what's the whole? What's the whole? How much is the whole? 14. And then just to not to trick you on this, outside is 5. What's the whole? Is it 5x or is it 5 plus x because we're short on time? Oh, I heard half and half. That's hilarious. It's actually 5 plus whatever x is. I heard some people say 5x. And then you just have to be a solver. Okay? So it ain't no thing. It's actually easy stuff. You just got to remember it. All right, now I don't have time for number 9, but it actually is easy. 9 over x equals 8 over 20, right? That's direct for me. Instead of trying to remember something else. 9 over x equals 8 over 20, crisscross. And then the last thing we actually already have, and I stole this off the internet. I love the internet. I just look for images, and some people have great stuff out there. So if it's out there in Google, we can use it, I think, or I could get sued. Who knows? I got no money, so it doesn't matter. A radius to a point of tangency. Didn't we already have this, by the way, in our last notes? I kind of threw that in there. Their tangent there. So you have actually some triangles and actually some Pythagorean theorem questions. Very beginning of that worksheet deals with the radius hitting the point of tangency, and then they have a triangle. It's Pythagorean theorem because you have a right triangle because of that right angle. But I just pulled this Mickey Mouse example. What's x? Well, these are points of tangency here. So these are right angles. This is that's a nice square there. What is the sum of 4 angles in a quadrilateral? 360. So what is x? It's simply as 360 minus 90 minus 90. So the point of this question is you had to know that those are right angles there. And then that's what x would equal. Okay, so then just as the bell's about to ring, which it is, the very beginning questions deal with a radius hitting a point of tangency, but it's actually a Pythagorean theorem question. All right, kind of scenario. Okay, so we'll see you tomorrow on Wednesday on our online day. Thursday, Friday is probably just clean up everything, man. I know there's a lot of stuff out there for the circle stuff, so I'll probably have some other thing. That worksheet is due Friday. I'm actually going to look at it, okay, for you guys. Thursday for the people that are Monday people. Okay, so make sure we understand that.